Okay, welcome everyone to the next DIPC community seminar. I'm going to be introducing Miguel today because Marek told me he couldn't make it. So it's my pleasure to introduce Miguel Moreno Ugeda, who's a well-known expert in STM. I'll very quickly review his trajectory. He did his PhD in Autónoma University in Madrid with Iván Grzelczak and José María Gómez. And then he was a postdoc in Berkeley in the group of Mike Cromie, where we also overlapped a little bit, also working in STM. And then he went on to have an Iker Basque fellowship in Nanogune in the group of Nacho Pascual. And then he got a Ramón y Cajal fellowship in the university. And then he was made Iker Basque associate when he got his first ERC to work on STM into the materials. And he's now Iker Basque professor at the DIPC with the second ERC on a similar topic on moirés. And yeah, we're very happy to hear about your work. So the floor is yours.
Okay, so good morning, everyone. Thank you, Fernando. Thank you, of course, to David and Marek for this opportunity to talk to this community, which is for me, of course, a privilege. So today, the goal today is to provide you with an overview of our current research activity in the group in the last 4 or 5 years or so, but as well as to show you some our technical capabilities, which might be of interest for some of you for different reasons. So heads up, this is, I've been asked to give a talk accessible to everyone. So don't expect me to get into details about any of the experiments that I will show you. I will just glance at them so that you can have a taste of what's going on in the group. But instead, please expect the introduction of very simple concepts that you may be familiar with. So apologies in advance. Okay, so let me introduce the group. So we are, as you know, an experimental group based here at the DIPC and the CFM. Our interest is the exploration of collective electronic phenomena that arise in low-dimensional materials in general. So I've prepared a list of the materials that we have worked on in the last 4 or 5 years. You can see that most of them are 2D materials that or have a strong 2-dimensional character. So for example, 2-dimensional TMD materials, moiré materials, iron pnictides, or TMD polytypes. But in the last year or so, we have extended our research activity towards non-strictly 2-dimensional materials, and we have explored heavy fermion compounds, pyrite, multi-insulator, or even cargo-imine materials. However, due to the time constraints today, I will just focus on 2-dimensional transition metal dichalcogenides and moiré materials, which anyways represents the 70% of our activity. Okay, so our methodology concerns 2 well-differentiated steps. The first one is the synthesis of the 2D material, and the second one concerns the electronic and structural characterization of the material that we have grown. For the synthesis, we follow 2 different methods: the molecular beam epitaxy, which is a bottom-up approach from the elemental sources, and the second is the nanofabrication, which is a top-down approach, which is consists of the isolation of the 2-dimensional layer from the bulk. For the characterization, we use mainly SPM techniques, for example, atomic force microscopy in ambient conditions and scaling tunneling microscopy in low temperatures in ultra-high vacuum conditions. Okay, so given the broad audience of this talk, let me get started by explaining how the STM works and what's the information that we can attain from the STM experiments. So an STM is a microscope, for the powerful microscope, I would say, for the visualization of metallic and semiconducting surfaces from the micron scale, as you see in this STM image, down to the angstroms scale, at which you can already see atoms, not very well in this image, but believe me, there are atoms here, or individual defects like this one, okay? So the working principle of STM is very simple. All you need is a very sharp metallic tip represented here, okay? Ideally finishing in one single metallic atom. And so if you need to approach it at a distance of about 1 nanometer or so to the surface that you want to explore, and then apply a bias in between these 2 electrons, like let's say 1 volt. okay? And then all you have to do is to keep that, well, if you apply a volt and you are so close, current, a tunneling current flows in between these two electrodes. And in order to scan these images, all you have to do is to keep the value of that, the magnitude of the tunneling current constant while you scan the surface. So basically you register the motion of the tip up and down, and that makes these STM images, okay? But the STM is not just a microscope. Okay, so we can do local spectroscopy in order to get information about the material or the surface that we are exploring. And the reason behind that is because there are three magnitudes that can be controlled externally. Those are the tunneling current, okay, flowing between the electrodes, the energy of the tunneling electrons, okay, controlled by the bias voltage that we apply, and basically the relative tip sample distance. Well, we have no control about the absolute, but the relative tip sample distance. Okay, so these three magnitudes are interplay and can be, can be expressed, or the relation between these three magnitudes basically is summarized in the tunneling, the current tunneling expression that was developed by Tershov and Hammond in the 80s. So basically you can fix one of them as a parameter, let's say, a current, and then study the interplay between the other two, okay? So by far the most known spectroscopy method is the IB spectroscopy, in which you hold the tip sample distance at a fixed value, and then you register the value of the current as you sweep the bias voltage. In this example, for example, the bias voltage is swept between -12 and 12 millielectron volts, and you see here the value of the current. However, I will show you that the way that this spectroscopy is shown and represented is the DITB instead of the IB. And the reason is because under certain assumptions, this value, which is it's called the differential conductance, can be considered as just proportional to the local density of states of the sample that you are studying, okay? So this is the way that normally these curves are represented. So all you have to know is that this is in general proportional to the local density of the states of the sample. So here, what I'm showing you here is the superconducting gap of lead, I think. No, niobium diselenide. And zero bias represents the Fermi level, okay? Okay, but so I told you that this value, the differential conductance, can be measured locally at the particular point where the tip is. So basically, this quantity can be mapped in real space with atomic resolution. Here I show you an example. So this DITB spectrum is taken on this particular point at the defect, where you see that it shows a gap. Okay, around the Fermi level. So imagine that we wanted to know what is the spatial localization of this peak. Okay, that peak is located at 26 millielectron volts. So what's the spatial distribution of the charge at that particular energy? So all we have to do is basically to set the bias voltage here and then map this quantity all over in the surface. And here's the result. This is not a topography image. This is a conductance map, a differential conductance map. You can see that at this energy, electrons are not spread homogeneously, are just concentrated here. Okay, this is just an example. Okay, and now let me get started with the molecular beam epitaxy materials that we grow, okay, with the experiments. So molecular beam epitaxy, it's a very versatile technique for the growth of thin films in general. So it's been known for many years, and of course can be applied to the growth of 2D materials. So this technique relies on the growth from the elemental components. So in this sketch, you can see, for example, 3 different sources: tantalum, niobium, and selenium, okay, from the elements. And it's usually done in ultra-high vacuum conditions to maximize the cleanness of the resulting thin film. In general, these elemental sources are heating the surface where the material is going to grow, or the thin film is going to grow. It's usually kept at high temperatures. It's usually hot, so that the kinetics and the chemistry can take place, and then that's the way to proceed with these materials. So in general, the growth of the material, in our case, we monitor it in real time using electron diffraction techniques. So there are new lines appearing as you grow the material that gives you information about the coverage of the material or the number of layers, et cetera, et cetera. So once the growth is done, you can check it, for example, with AFM and check the morphology of the coverage of the material, et cetera, or STM, of course. So here I show you a picture of our MBE instrument, which is a homemade instrument, and it's particularly suited for the growth of selenium-based 2D materials. So once we have these samples grown, we basically cap them with an amorphous layer of selenium, and then we can transport them to anywhere. So the closest place to go is, of course, our STM next to our MBE, but we have sent these samples to Denmark, US, etc. And they survive. You just anneal them, you expose the crystalline material, and then you can work with them. So I take this opportunity to introduce you to our former postdoc and responsible for this line, who is Wenwan, and the present times are taken care by our postdoc Haoji Eguo and Sandra Sejan. They are responsible for these epitaxial materials and other lines. So we are here in the audience. Okay, so with this technique, it's very versatile, and we can grow many different materials with many different electronic properties. So here I show you an example. For example, we have grown, and this is one of our favorite, semi-metal, which is graphene. We have grown tin selenide, which is a ferroelectric. We have grown the 1T prime phase of tantalum disulfide, which is a quantum spin hole insulator material. And of course, charge density wave and superconductor 2D materials, here represented by titanium diselenide. You see the charge density wave here and the superconductivity. This is a monolayer of iron selenide, okay? So, but we can go beyond that with MBE. And the beauty about MBE is that, of course, that we can grow the bare 2D material. So here's a list of the materials that we have grown in the last years, but we can go beyond that. For example, we can tune some of the properties of the material by growing an alloys. For example, mixing niobium and molybdenum. I will show you in a second a little bit about these experiments. And of course, we can grow as well vertical and lateral heterostructures, okay? So the properties of these individuals are different from the material when it's stuck in a vertical position. I will show you an example of this as well. Okay, so these are the three examples that I want to show you today. I will briefly talk about the superconductivity that takes place in a single layer or monolayer of niobium diselenide. I will describe the superconductivity and the charge density wave of a two-dimensional TMD alloys. And finally, I will briefly mention one recent experiment that we have carried out in a two-dimensional condol atom. Okay, so let's get started with a single layer niobium diselenide. So here I show you a large-scale STM image so that you can see the typical morphology of our samples. This is an image taken at, I think it's 4 Kelvin probably, where you can see two silicon carbide steps. Okay, so you look at this one, for example, the dark parts is the graphene, the substrate. Okay, and these islands are the island of isolated niobium diselenide. Okay, so you can see that the typical size of the island for this particular coverage is around 200, 300 nanometers or so. So if you now take a look, you could take a closer look at images with atomic resolution, like in this one, you can see that apart from the atomic registry, there is a supermodulation that corresponds to the charge density wave, which is basically preserved with the same periodicity, which is a near commensurate 3x3 periodicity in niobium diselenide. It's preserved in the two-dimensional limit. See what happens with the, oh, yes, and in terms of bond structure, the niobium diselenide, or in general, any TMD has a very simple band structure. In the case of niobium diselenide, there is only one band crossing the Fermi level, and ultimately the only band responsible for superconductivity. And the only well, it has a D band, a D character, okay? And so it's coming basically from the niobium atoms. And it has a characteristic spin splitting around the K valley. And the reason is because the huge spin orbit coupling in the monolayer limit. Okay, concerning superconductivity, this material is superconducting both in bulk and in the monolayer. Okay, so these are very old findings from the 80s or the 90s, where you can see that the bulk 2H naive diisonite is a multi-band superconductor. Here you can see the two band gaps. Here is one, there is another one here, and the critical temperature is around 7 Kelvin. Okay, so if you grow just one layer of the materials, here's the result. The system is also a superconductor, but with a much smaller critical temperature, around 2-3 Kelvin, depending on the method that you grow it. It's not entirely clear whether it's a multiband or not superconductor, but this is very nice because I will introduce you here. So by the time we were looking at this gap, something that brought us our attention was the existence of bumps outside of the gap. Okay, so these are the coherence peaks. This is the gap. And what we did not understand was the systematic presence of these peaks outside of the coherence peaks, but they were everywhere. So I'm showing you 4 different curves taken in different regions with different tips, okay? And you can see that always around the superconducting gap, there are these peaks at both occupied states and unoccupied states. In general, they are symmetric with respect to the Fermi level. So if you find one here, in general, you find another one here. You can see there are series of these peaks. So we put this into numbers. So we basically did a histogram counting the number of peaks that we used to see in statistically different curves, DIPC curves. And here is the result, okay? So the first peak in the histogram corresponds to the coherence peaks. So no surprise, the distance between the Fermi level and the coherence peaks gives you more or less the superconducting gap, which is around 0.4 millielectron. But if you continue, there are certain peaks that can be extracted from the histogram. And surprisingly, so we saw the position of the maxima at these energies, 0.5, 1, and around 1.5 millielectron. But it seems like if there was a fundamental mode and some harmonics followed after that. So what's the origin of these peaks? In order to make sure that these peaks were related to superconductivity, what we did was to increase the temperature and repeat the experiment at the same location. And you can see that as we approach the critical temperature, basically these peaks are gone. Okay, but the same happens if we apply a magnetic field and we approach the upper critical field in this superconductor. Basically, these peaks are gone, even at temperatures as low as 300 millikelvin. So these two experiments or these two measurements demonstrate that the origin of this peak, the nature, ultimately has to be the superconductivity. They are related to superconductivity. So I don't have time to get into details, but what we believe is going on here is basically we are observing soft superconducting collective modes. In particular, we believe that we have visualized Leggett modes. Leggett modes is a particular type of a soft superconducting mode, collective mode, which arises from the competition of 2 different superconducting channels. Okay, so Fernando, Paco, and Daniel have modeled this particular system where you can see that only the K pockets are considered. In principle, the S-wave singlet, which is this wave, is the leading term, okay, in the superconducting state. But there is a subleading channel, which is enabled by the structure of the Fermi surface, which is this one, which is an F-wave channel. It's a triplet channel, okay? So in principle, these two guys are competing each other, and that normalizes the density of states outside of the gap. So the spectral function changes from this blue curve, which is the typical decay of the coherence peaks, and it's normalized so that some peaks appear. And actually, the strength of the triplet component is not that small, because this is the ratio between the location of the fundamental mode, normalized to the size of the gap, which is experiment gives this value. So that means that the strength of the triplet component is not far from the singlet component in our case. Okay, so that's it with respect to the single niobium diselenide. So is there a way to tune the superconducting state and the challenge situation state in using molecular beam epitaxy? So the answer to that question is yes. You can mix different compounds in order to play with the properties of these materials. So here you have niobium in the periodic table. It's surrounded by different materials. So each column here that I'm representing are isovalent elements. Okay. So for example, titanium or chromium are allovalent elements with respect to niobium because they have different valences. Okay, so what we have done is basically to merge in the same material niobium with titanium, which titanium has one less electron in the valence band, and molybdenum with respect to niobium has one more electron. So in other words, this is gonna play the role as a whole dopant, and molybdenum, it's basically the opposite. It's going to be electron doped. Okay, so I'm going to skip the part of the titanium because it's a bit complicated, but let me talk to you. Well, this is more or less what we have done, illustration of what we have done. We have gradually increased the number of molybdenum and titanium atoms replaced by niobium in this plane, okay? And this is the expected effect of the molybdenum. So if you go to the molybdenum, as you add more and more molybdenum, basically you electron dope it. And in this case, in principle, the density of states decreases. Okay, so if you dope it with titanium, the effect is basically the opposite, because this is the density of the calculated density of states, and in principle, you are basically increasing the density of states at the Fermi level. Okay. As I said, I will only mention the molybdenum case. So here I show you an STM image of a very dilute concentration of molybdenum atoms that can be recognized easily. So do you see these triangular features here? You can basically count them. And so each of those triangles represent a molybdenum atom. And the reason why we see it is basically because the presence of a molybdenum atom here basically changes a little bit the density of states of these upper and lower atoms. It is what we see. We don't see the transition metal plane, but we see the selenium planes, and basically they are a little bit different, and then can be counted one by one. Okay, so here I show you our journey from niobium diselenide to our first alloy. Here there is 4% of molybdenum atoms. So basically with 4%, you can basically count one by one. So things change, of course, if you add 20% of molybdenum atoms, then you cannot count them, or 70%. Now the minority is the niobium, and we are closer to the semiconducting phase. Here, it's close to molybdenum with just 6% of niobium, and now you can count niobium atoms, individual atoms, and this is the final, the end of the journey with MOSE2. Okay, so I'm showing you here a set of representative DIDB curves where you can see the evolution from the metallic superconducting challenge to wave state here up to the semiconducting state. So we're able to basically track the changes in the electronic structure in terms of the metallicity, that's the superconductivity, the challenge to wave, and the emergence of the semiconducting gap. Some of these features that you see here correspond to some features in the band structure. So can be directly identified. So for example, E2 represents the distance between the Fermi level and this distance. E1 represents the distance to these P bands, et cetera, et cetera. So I'm not going to get into details, but basically you can see, for example, as we add more and more molybdenum, this peak basically disappears or vanishes, but while crossing the Fermi level as well. And for an amount of 70% of niobium, the gap starts opening here. For 80%, the gap is considerable, I mean, significant already, and then ends up with a gap of 2.2 electrons. This is what I'm showing here, basically. Or you can see that how it's reduced, right? So the metallicity changes here for 70% of molybdenum. 70% of, yes, molybdenum. So concerning the superconductivity, here's the evolution with the molybdenum doping. Interestingly, basically, superconductivity of the superconducting gap has a tendency to increase at the beginning and then drops. Okay, so you can see it here. You can see that this gap, for example, is larger than this one or this one. The reason behind it is that we believe that what's going on here is that as you add more and more molybdenum, you reduce the density of states. Okay, so this material is close, is at the verge of being magnetic. It's very close to being magnetic, but it's not. So we expect that the magnetic fluctuations are very strong. So if you decrease the magnetic, if you decrease the density of states as you add molybdenum, what happens is that these magnetic fluctuations are decreased, which are pair breaking. And that helps a little bit the superconductivity to thrive a little bit. Eventually, of course, the disorder and the reduction in the density of states wins and kills the superconductivity, but superconductivity survives up to 15% of molybdenum atoms, which is significant. And something similar happens with the challenged wave. Let me skip the explanations here, but basically what I'm plotting you here is the intensity of the 3x3 peak in the FFT. And you can see it's very noisy because it's tip dependent. But you can see that basically the evolution is very similar, and somewhere in between 15 and 20%, the challenged wave is killed due to disorder. Okay, so we have repeated this experiment using, instead of niobium, using tantalum, and instead of molybdenum, we have used tungsten. And the reason we have repeated this experiment is because tantalum diselenide is not superconducting in the monolayer limit. In the bulk, it is. But if you reduce it, if you shrink it to the monolayer limit, it's not superconducting, at least to 300 millikelvin. While, by the way, it preserves the challenged wave. Here you can see the challenged wave. It's like in bulk, but it's not superconducting. However, the band structure of this material is very peculiar because the Fermi level lies right here, very close. So these are by the way, these are the two bands of the band I told you before around the K valley. So these are two spin polarized bands. Okay, so there is one crossing the Fermi level, but it's not enough to trigger superconductivity. But the Fermi level is super close to the other one. Okay, so we thought, okay, let's put a little bit of tungsten atoms and let's lift the Fermi level here. Okay, so here you have an STM image of tantalum diselenide, and again, these triangular features correspond to tungsten atoms. Okay, and here you have the superconductivity. We're basically able to trigger superconductivity, and as soon as we put a little bit of 1% or 2% or 3% of tungsten atoms in the lattice, then we develop a superconducting dome, as you see here. So the superconductivity is not very strong. In the optimized critical temperature is around 1 Kelvin, but yet here it is. Okay, and then as it happened before, due to disorder and the density of states, basically at the end is killed. But here it is. And there are predictions, by the way, about what's going on if you generate superconductivity right here. The problem is that the superconductivity that we generate is close temperature, and we cannot resolve it with the system that we have in the CFM. So I will repeat. Something really interesting about tantalum diselenide is that if you grow a sample like this one with a little bit more of coverage, okay? So in general, the first layer that grows next to graphene, in general, is the 1H tantalum diselenide, okay? So this is the one I told you about. It's just a metal. It's not superconductor, but you can see that if you increase the coverage, in many occasions, there are like triangular features on top. Those are the bilayers, okay? So the second layer is starting to grow. And for some reason that we don't know, but it happens, in many occasions, it grows a different phase. Instead of the 1H phase, which is a polymorph of this material, it grows a different phase, okay? So what we have here, it's a bilayer. One of them is the 1H phase, and on top of that, we have the 1T phase of tantalum. Okay, so what's nice about this bilayer? So this bilayer represents the first, I think, experimental realization of a two-dimensional condor lattice. Condor lattice has been studied for decades in 3 dimensions, in 3-dimensional materials, very complex materials with very crazy stoichiometries. So, but now we and other groups have found that this is a great platform to study condor physics in 2 dimensions. And the reason is because what you are seeing here are not atoms. What you are seeing here are clusters. These triangular features are clusters composed of 13 atoms, okay? So this is a challenged wave. This is a challenged wave in which, due to the band structure, basically, there is a lone pair electron confined within each of these triangular features. And that lone electron basically, in the ideal case, develops an isolated magnetic moment of 1 spin 1/2, okay? Okay, so you can see this as a 2-dimensional condor lattice where the 1T layer basically hosts the spin lattice, okay? In direct interaction with the metal, the 1H phase represents the electron seed, the electron pool of conduction electrons with which these individual magnetic moments interact. Okay. So what we did, we basically studied the ground state of this collective phase. Okay. So if you look at the literature in the past, basically you immediately find the Doniak phase diagram that it's simplified, but it's shows looks like this. Okay, so at high temperatures, what you have are individual magnetic impurities. Okay, just screened by the metal. But if you keep lowering the temperature, eventually there are 2 ground states that can be accessed, and that depends on the strength. On the density of the states and the strength between the conduction electrons and the single impurity. So J represents the strength interaction between the magnetic moment and the conduction electron. Okay. So depending on that strength, you can get to a condor insulator regime, which is a paramagnetic solution in which basically all the spin lattice is basically screened by the material. And if that's not strong enough, then you access a magnetic order solution, okay? And this can be studied through the density of states, which is that exactly what we are good at. In the condor insulator solution, in principle, you expect 2 bands to play all the game here. So this purple band represents the conduction electrons, and the green band, which is more localized, represent the magnetic moments. Okay, so the interaction between these two bands lead to the formation of 2 bands around the Fermi level. And basically a gap called hybridization gap opens at low temperature. So this is the signature of coherence, okay? So these 2 bands are hybridized, and basically we are in front of a condo-insulator regime. So the magnetic order, it's similar, but it's not the same. So there's interaction between these two bands as well, and new bands arise from this. There is an increase of the density of states at the Fermi level. There is basically the formation of a gap-like feature as well around the Fermi level. So these two guys are pretty much the same, okay? But you can see that this is true as long as you don't apply a magnetic field. There's a key difference between these two band structures, which is that these bands in the condo insulator ground state are spin degenerated. Okay, so have the two flavors. Whereas in the magnetic order, they are spin polarized. So if you apply a magnetic field, there should be a difference, right? Because in one case, if we apply large magnetic fields, we should be able to split these two peaks into two flavors, whereas these are spin polarized. So therefore, all we're gonna get is basically splitting due to Seebeck effects. Okay, so that's what we did. Basically, again, this is a DIPC curve, local density of states, taken on top of one of these Star of Davids, these triangular features that I showed you before. And this is how it looks. There's a huge increase of the density of states at the Fermi level, and you can see there is like a gap-like feature exactly center of the density of states. So no surprises, which is what we expected in terms of density. However, see, if we now apply a magnetic field, things can be. I mean, we can distinguish between these two phases. So this is the curve in black. This is the curve for 0 Tesla, and we can gradually increase 1, 2, 3, 4, 5 up to 11 Tesla, and you see that basically that all it happens is basically that the maxima of these peaks get open and open and open. So there are no new features showing up. There is a gradual separation of the peaks. So this observation, along with others that I'm not showing here today, allow us to discriminate between these two, and this is the only. So we believe that we are this system goes to a magnetic order, or there should be some magnetic order. We are, by the way, trying to doing this experiment with a spin contrast. This is something that we will show you in the future. So this is pretty much it I wanted to show you about these epitaxial materials. In the last few minutes, if I have time, Fernando?
Yes.
I'd like to show you another strategy that we are following in order to create 2D materials, which is called nanofabrication, okay? So why we care about nanofabricated samples or 2D materials? So you can imagine that there are pros and cons of nanofabricated samples with respect to molecular beam epitaxy, but there is one key difference between them. And one particular advantage of nanofabricated samples is that is the only technique that allows us to get these kind of samples. So what I'm showing you here is a heterostructure, a vertical heterostructure, composed of 2D materials rotated at a specific angle that we decide at will, okay? And that's something that in general cannot be done with molecular beam epitaxy samples. So you can induce a moiré pattern. This is a moiré superstructure, and this is something that you can do using MBE samples, but not you cannot do it at will. So it's what it is, kinetics, order, rules, the growth, and basically you cannot control that. And this is something that with nanofabrication you can do, okay? So the origin of the motivation for us to do this kind of samples is the following. So 5 years ago, more or less, it was discovered that 2 layers of graphene rotated at a specific angle is enough to trigger a very complex and rich electronic phase diagram, including superconductivity, multi-insulator, orbital magnetism, chain insulator phases, etc., etc. Of course, none of these new phases take place in bare graphene. Okay, so you just basically simple put one on the other, and then you rotate like one degree or so, and then magic happens. So the origin of this spectacular phenomenon is the following: is the flattening of the bands as you rotate in between. There is some superpotential that the electrons feels, and then the effect on the band structure is the flattening of the bands down to energies that are comparable to the Coulomb repulsion, which is around 10 milli-electron volts or so. And that Coulomb repulsion, and that triggers strong electron correlations in the materials and all this at the end, okay? So this is something that we wanted to study, in particular because superconductivity, but also other correlated electronic phases, has been demonstrated in the last 4 years or so that it's not something that arises by chance, or it's not, so it's a very robust collective phase. Superconductivity in particular has been observed in 2 layers, in 3 layers, 4, 5, other stackings as well. So it's there. And nowadays people are getting even higher critical temperatures. So these platforms are many different platforms in which you can study superconductivity and other novel collective phases. But even when we know that superconductivity and these phases are there, in general, there is the origin, the nature of the superconductivity, in particular in moiré materials, remains a mystery. So, for example, regarding superconductivity, there have been many theoretical works trying to explain why superconductivity emerges here. Some of these works have considered the plausible symmetries and different pairing mechanisms that have never been observed in nature before. Okay, in particular, this is due to the large number of degrees of freedoms in these systems, being valleys, sublattice, etc., etc. It's a complex problem, but the physics stored in it is promised to be nice, very nice. Okay, the problem is that experimentally speaking, so all the information that we have nowadays about these systems, in general, comes from transport experiments, which are outstanding. They provide a lot of information, but they lack of information at these scales. This scale is the atomic scale and the moiré length scale. And here is these length scales are very important and they cannot be missed if you want to ultimately understand the superconductivity, for example, here. Okay, so you can imagine that at these scales, the STM is expected to play a very large role. Okay, so for those of you unfamiliar with this kind of technique, I will just mention that the way to fabricate these samples is the mechanical exfoliation. Simple as that. You take one Scotch tape, you approach it to a valve, van der Waals material, you remove part of it, okay, because it basically sticks on you. And then you repeat this several times, 4 or 5 times. There are different recipes and opinions about it. And so once you are happy with it, all you have to do is to stamp it on a particular substrate, in general silicon or silicon oxide. And then you look at the debris that you have left on top of it. So here I show you an optical image that you can see the debris. This is, I think this is graphene or graphite. So these are debris of graphite, thin films of graphite, etc., etc. But if you look carefully, there are subtle regions that can be potentially very thin down to a monolayer. Okay, so this was first done by Kostian Oboselov and Andrei Gaim back in 2004 for the first isolation of 2D materials. In particular, they did it for graphene, niobium diselenide, molybdenum diselenide, or even visco systems. Okay, so here you say, of course, you know that this was awarded with the Nobel Prize in Physics. Okay, so we basically use this technique. Let me take this opportunity to show you the lab that we have, the nanofabrication lab that we have at the Tandem building at the DIPC. And basically, we have some optical microscopes and transfer stage in order to manipulate these flakes, okay? And of course, to introduce Casey Underwood and Johnson Wang, who are the responsible for these laboratories. They are working on it. Johnson is in particular here. Okay, so this is the lab where we are trying to grow our samples, okay? So I'm gonna show you in the last couple of minutes our latest progress on this. Here, I show you a graphene flake. We know that because the optical contrast and the AFM images that we take, we know it's a monolayer, okay? And it's actually a large one because it has like more than 100 micrometers in length. So it's perfect for growing this thing. So the first step, if you want to rotate 1 degree, we need first a single crystal, okay? Because we assume that the crystal orientation here and here and here is the same. It's gonna be the same, okay? So the strategy is to cut it. Here you can see the cut of the graphene flake. There are different recipes to do that. I think for this particular one, an AFM tip was used to cut it in two, okay? So now we have 2 graphene flakes, one and other 2. They are independent now, but they have the same crystal orientation. So what I'm showing you here is that top view of this device where we have the graphene. This is a crystal that has some polymers like a rubber. And then at the apex of this device, we have a thin film of boron nitride. The boron nitride is this pink hexagon, okay? And that helps us to pick up our material. So you can see that in this particular case, the pink, the boron nitride flake is ready to pick up the upper part, okay? And this is the result, that the upper part is now removed. Now it's in the boron nitride flake. And what remains here is the second part, the second flake, okay? So now this is the right moment to rotate, okay? So we rotate and we approach the substrate again, and we pick up the second flake. The angle or misorientation has been introduced in between these 2 steps, okay? So this is the result. This is one of our first twisted bilayer graphene stacks that we have on top of the boron nitride substrates, etc. And in principle, theoretically, they show a mismatch of 1.1 degree. So of course, we are not basically constrained to graphene. We are using other materials. So here I show you another example in which we have, these are not monolayers. These are thin films, ultra thin films of MOSE2. And the idea here was to stack them on top of the other, okay, at 0 degrees. This is what we call marginally twisted because it induces anyways a rotational disorder, even if you stack them at 0 degrees. So basically what we have done here is to pick up this flake and then by tearing from here, and then we put it on top. And you have the optical image here of the resulting flake and the corresponding AFM image that shows the resulting heterostructure. So you may have noticed that we have this setup inside of a glove box. So in order to do the examples that I show you with graphene or even MOSE2, it's not necessary to have a glove box because they are inert materials and there are other strategies to clean them up after the fabrication. However, we are keeping this setup inside a glove box, and the reason is because we want to. Our goal is to extend the moiré exploration beyond graphene. For example, I give you an example here. We are pretty much interested in semi-metals and semiconductors. Here I show you, for example, one of the very first attempts to isolate ultra-thin films of titanium disulfide. Okay, And what is left here is a UHV chamber that we are building right now here on the left in order to transfer the devices from here to UHV in order to cut them, clean them, and prepare them in general for the characterization that will take place in this new microscope that is about to come next year. So the base temperature of this system is gonna be a bit lower, well, a bit lower, quite lower than the one that we have. So it's going to be the base temperature of 30 millikelvin. We expect to have energy resolutions around 20 microelectron volts. So we would like to live here somewhere. Okay, and the idea behind it is not just to have a better resolution in order to unambiguously characterize these systems, but also to access domes that have never been explored. Okay, or who knows, maybe there are new phenomena arising at these temperatures that nobody knows. And with this, let me just wrap up by thanking my colleagues at the group. Here I show you the past and the present of the group, Wen Wang, Paul Dreher, and Rishabh Hart, who were fellows in the group at the very beginning of the group. And the upper row is the present. Sandra and Youngsong are doing their PhD in the group, and Casey Underwood and Hao are in their postdoctoral state. And of course, I would like to thank my colleagues in our community who somehow, one way or the other, contributed to part of what we have done in these years. The DIPC fellows, the people from the CFM or the university, and of course the Nanogune, as well as our external collaborators around the world. And that's it. Thank you so much.
Thanks for the beautiful talk. Are there questions for Miguel? You can also ask questions in the online audience if you want. We'll be checking the chat. Danny?
Can you comment a little bit on the capabilities within the laboratory structures? You mentioned at the very beginning that they are
Lateral.
lateral.
So we have only grown one. I think it was a superconductor. It was niobium diselenide and then titanium diselenide. The way to go in these epitaxially grown samples is to grow one of them, then stop the growth and continue with the other metal. And then in general, the growth of the material continues with a different transition metal element. And so, for example, if you grow niobium diselenide, you have islands, superconducting islands, and you can get these islands surrounded by something that it's not superconducting. So we have grown only niobium diselenide and titanium diselenide, and they show a beautiful interface between the two.
Beautiful word. I have lots of questions, but I'll only ask you one. So this is the one where you had the 1H and the 1T tantalum diselenide. And there, when you have the chondrolattice, and you were saying those clusters had 13 atoms in there. Why 13? I mean, you probably have a moiré pattern, right? In this, you probably have the need to have that one lone electron. So somehow is the 13 atom cluster connected with all of this?
Well, that's the grounded state of the Charge-in-situ wave. It's called the Star of David. So there are 13 tantalum atoms involved in the unit cell. Okay, so each of them contributes with one electron. So there are 12 atoms that are occupied, but there is one. There is one alone.
So that's why you need
the one that develops the magnetic moment. Yes, it's a well-known. I mean, in bulk, this particular Charge-in-situ wave also develops exactly the same. Has been studied for years, but if you grow it in 2 dimensions, the same Charge-in-situ wave appears.
So your photonic monolayers are grown on graphene monolayer, bilayer, whatever. So I guess then necessarily your results are affected by that. And also the band structure that you showed has to include the substrate on top of the layer.
Yes, so this is something that I did not mention. Of course, you grow these materials on something, and that something may play a role, okay? So we normally grow it on graphene because everything grows on graphene, everything. But there are other substrates, for example, boron nitride, gold element. Graphene, it's a metal, so it's basically affecting superconductivity, for example, somehow. But we repeated the experiment on different substrates, and we noticed that the critical temperature and the gap, et cetera, all the properties that we could measure on graphene and on other more insulating substrates, such as, for example, boron nitride, it was identical. So graphene, even if it's a metal, it's a low density, it has a low density of state, and therefore probably the impact on the superconductivity is very low, very low.
Second question, if I may. You showed on that condo system, what exactly, where is this non-dispersing band coming? So you have itinerant states.
Well, it's a localized electron at each star of David. That's what this band represents.
So it's somehow self-localized.
It's localized at the center of the Star of David. Yes, that's why it's so flat. So ideally, it crosses the Fermi level and remains there. So the magnetism arises as long as that band remains crossing the Fermi level. Otherwise, it gets filled or empty. Of course, magnetism disappears.
Then shouldn't you get that same band in every Star of David CDW?
Yes, yes, yes.
But this is never observed.
Why not?
It wasn't.
I don't know if I have. It's probably I don't have the.
I mean, at least in potentiation, nobody saw this.
Well, the transit wave has to be developed. Otherwise, you don't see it, of course.
Of course.
Oh.
There is nothing you.
No, I went to. Okay, I don't have the spectrum here because all I show is this one, but we have other curves at a larger energy window in which we see basically the feature of the band here, and the corresponding one. I don't have it here.
What's the bandwidth of that?
I don't know, 100 milli-electron volts or so.
It's less, 30 or 40 at least. But a key difference from ARPES is that those are bulk experiments, and the stacking of the charge density wave matters a lot. Because there is hybridization between bilayers, and that you don't have here.
Why should there be a difference?
Because of
Because
the
it's a
stacking
one
of the transit wave.
monolayer. So there was another question here.
Yeah. One of your last slides where you have all these setups over the world, and then yeah, you put DIPC and so on. Can you show it?
That's it coming. This one?
No. Previous one.
Previous.
Hey, that one. Yeah. Go ahead. The one with this chart, right? Yeah. What is this dotted line?
The dotted line.
Yeah.
Okay, so what I'm plotting here is the sample temperature. So each dot represents an STM system. Okay, placed in, I don't know, NTU, Max Planck Institute, etc., etc. So this is the sample temperature, and this is the electronic temperature. The electronic temperature of the system cannot be smaller. I mean, cannot be lower than the sample temperature. Okay. okay? So the idea, if you work in one of these millikelvin systems, is to have to work at a sample temperature as low as possible. But that's not it. That's not the end of the story, because you can have a 10 millikelvin system, and then your electronic temperature, due to radio frequency noises, et cetera, can take you here. And basically, you don't care. I mean, you don't care if you are working at 10 millikelvin if you have a noise that takes you here. Effectively, you are working at much larger temperatures. So what I'm plugging here is basically the declared ratios between the sample temperature and electronic temperatures of the systems I'm aware of.
But you can always train your system to avoid the electronic tension.
Yeah, that's extremely complicated. And that's why some people work at 10 millikelvin and then effectively, so this is so one of the few papers on bilayer graphing have been done with this system, superconductivity, which is very nice work. But the temperature, the sample temperature was 20 millikelvin, but the declared electronic temperature, the effective temperature, is more than 200 millijoules. So an order of 10 above that. So if you optimize that, you can improve the resolution a lot. Okay, but you have to be careful. Otherwise, it's like working at 2 Kelvin.
I have another question.
Okay.
Yeah, your new samples, your new
Fabricated.
yes, fabricated samples. If I understand right, you prepare the sample and then you move the sample to a different chamber for STM or whatever. But how you find the little crystal that you produce, the rotated?
Yeah,
crystal and so on?
that's one of the main issues. So, for example, so this is like 5 micrometers across. Okay, so it's a very tiny dot in the middle of a large substrate. So how to find it? There are 2 main strategies. One of them is to use capacitive motion of the tip. Instead of tunneling, you can basically measure the capacitance between your tip and the substrate. And then you have some sort of contrast because the tip is safe. Okay? And you can scan it on metallic or semiconducting surfaces, no problem. But when you are on a metal or when you are on a semiconducting part, the capacitance between the 2 changes. And that is a way to image the surface. So if you have a pre-patterned circuit on your substrate that is giving you some indication of where you are and where you have to go, then it's a matter of time to find this. So this has to be located in a very precise location in the substrate with some indicators that take you like, but this is the direction to go. So you image it, you look, it's like, okay, we have to go to the right. How many steps? Boom. Then you look again, And there are 2 ways. So the capacitive imaging or the tunneling. Tunneling is nice, but it probably takes longer, but it's safer. So we are trying to develop both possibilities to eventually do it. It has been done. I mean, it's not new. People have done this for 10 years already. Not many people, but people can do it. So the problem is that if you have optical access, then it's okay. You can, if you had optical access, like in this image that I showed you at the beginning, then it's not a problem. It's, I think I used one of the, here. So this is the surface. These are some crystalline, micrometer size crystals. And this is the tip. This is the this is the bias pad or the gate pad. And this is the reflection. Okay, so the tip is precisely on top of one of these flakes. That flake might be like 50 micrometers or so. But if you have optical access, you can precisely move the tip. Otherwise, you have to rely on this capacitive imaging, which.
But that is, you can take any piece, right, that you land on. But in the one that you have been doing this moiré pattern, this is a single one, right?
Oh, no, of course. So our device will be on top of this. Exactly. So this is the boron nitride flake, but our sample is even smaller than that. But if you are able to put your tip on top of the boron nitride, I mean, you're so close.
Okay, okay.
But the problem is that in our cryostats, we don't have optical access, so we cannot play this trick. I mean, this is okay if you measure at 4 Kelvin, then it's okay, but to have optical access, otherwise.
Okay, so it's 10+1, so unless there is one last question. Okay, so let's have the last one.
So if you make this trick with your MB grown samples and cut them and then twist them, potentially get much larger.
Yeah. Yes. Oh, but this is a good example. So you're talking about removing the 2D flake here. I mean, yes, we could, but that would probably imply chemical methods. So if you grow MB samples in general, you have bilayers already, so it's not. And the way it grows in MB, you know that it grows like in tiny islands that eventually coalesce. Okay, so it's not a single domain like in the exfoliated samples.
Rotationally, they're
Depends on the substrate. I agree. But in this, for example, in this particular case, the naive disenlite grows at 0 and 30 degrees, but there is some sort of disorder. So if you want a twisted layer, there is some uncertainty that you have to.
they're probably more bonded than these flakes. So
And that's something.
That's the person.
Probably, yes.
Okay, so if there are no more questions, we can thank Miguel again.